I wanted to work through an example that involves inductors and energy stored in inductors. If you remember back to capacitors, we could think about capacitors as devices, circuit devices that store energy when we apply charge to the plates of the capacitor. And we can think of inductors as devices, circuit devices that also store energy when we pass a current through the windings of the inductor. So both capacitors and inductors store energy. In the case of capacitors, they store it in the electrical field in the capacitor. In the case of the inductor, they store it in the magnetic field in the inductor. In this particular example, we have an inductor. Maybe it's a solenoid, or maybe it's a coil. We don't know the geometry. We have an inductor. It's carrying a current of 1.7 amps, and it stores 0.3 millijoules of energy. And from that, we've got to calculate its inductance, its self-inductance. And then once we've got the self-inductance, we'll imagine that we increase the current in the inductor to 3.4 amps. And we're going to calculate the stored energy in that case of 3.4 amps current. So there's two parts here. So the first part is to find the self-inductance L of the inductor. And I'm going to use that relationship that we just talked about for an inductor between the current that flows in the inductor, I, and the energy that's stored in the inductor, the potential energy. And that's represented by this equation here. And if you look at that equation, it involves the inductance of the inductor. So for a given current, if the inductance is greater, you're going to store more energy. For a given current, if the inductance is smaller, you'll store less energy. In our case, we know the current, we know the energy. We can rearrange this equation to be an equation for the self-inductance. It'll be twice the potential energy divided by the square of the current. And then we can just go ahead and fill in the energy and the current. So we've got 0.3 millijoules of energy, and we've got a current that is 1.7 amps. And if we carry out the calculation, I got 0.21 millihenries. Just a remark about that, a couple of remarks about that. So henries are the units of inductance, self-inductance, named after that American scientist that uncovered the phenomena and worked with the phenomena of induction. Also, a second point is that when I fed in the energy, I fed in the energy in millijoules, and because I've filled in the energy in millijoules, my answer is in millihenries. If you prefer, we could have written the energy as 3 × 10⁻⁴ joules, and then our answer would be in henries. It would be 2.1 × 10⁻⁴ henries. Anyway, that was the first part. Second part is, we imagine we've increased the electrical current from 1.7 amps to 3.4 amps. And we want to calculate the new quantity of energy that's stored in the inductor. So again, we're going to use this equation that relates the current flowing in the windings of the inductor to the energy stored by the inductor. In this particular case, we actually now know the inductance, we know the current. We're using this equation to calculate the energy. So we no need to rearrange it here. All we got to do is fill in the inductance that we just calculated. So 0.21 millihenries, and multiply by the square of the new current. It's 3.4 amps squared. And if we multiply these quantities together, then we get the energy that's stored. In this case, the energy that's stored, I've worked it out, is 1.2 millijoules of energy. Again, I played this trick where I fed in the inductance in millihenries, and so the energy is in millijoules. I could have put in 2.1 times 10 to the minus 4 henries, and then I would have got 1.2 times 10 to the minus 3 joules. Either way is perfectly fine. And so this is the answer for the energy. Now, there's an interesting point here. I went through that calculation of using that the energy is 1/2 Li squared. But in some sense, I could have done it another way, a different way. And I could have just said that, oh, I noticed that the current 3.4 amps is simply twice the current of 1.7 amps. So the current doubled from the 1.7 amps to the 3.4 amps. And since the energy depends on the square of the current quadruples, and so the energy quadruples. And so when we change the current from 1.7 to 3.4 amps, that's doubling the current, you'll notice that we change the energy from 0.3 millijoules to 1.2 millijoules. That's multiplying by 4, quadrupling the energy stored. So we could have noticed that the current doubled, and then that would mean that the energy quadrupled. So that would be another way of solving this problem. Anyway, I wanted to just work through that quick example to remind us partly that the way we think of inductors and capacitors in electrical circuits is, or at least one way we think of conductors, capacitors in electrical circuits, is they are devices for storing energy. And in the case of the capacitor, the amount of energy stored is related to the charge on the plates of the capacitor. In the case of the inductor, the energy stored is related to the current that's flowing through the windings of the inductor. And this was just an example of applying that understanding, using that understanding about inductors, like we've used a similar understanding about capacitors in the past.